Welcome to MzansiNumerics. Today we are focusing on a bouncing ball, which is problem type 4. On the last video we were focusing on problem type 3. So problem type 4 is somehow similar to problem type 3 and also problem type 2, because the very same way that we deal with each bounce is the very same way that we are going to deal with a ball thrown vertically upwards and comes back to the same position, and the very same way that you are going to deal with this section in which a ball is thrown up from the top of the building, and then when it comes back the thrower is unable to catch it and then it comes back, because they are the same arcs. So they somehow the same interpretation or the same principle that we put in here, we are going to also apply it here. Let me clear my space so that we can discuss each and every variable of a bouncing ball. So now is problem type 4, which is a bouncing ball. So what do we have to know about a bouncing ball? A bouncing ball, let me draw its motion. Let's say there's a ball which was thrown downwards, then this ball hit the ground, and then now after it hits the ground, it goes up to a certain height, which is this one, and then it comes back to the same position, and then it goes up again to a certain height. When it goes to a certain height, and then it comes back to the same position. So this is a bouncing ball. So you have to understand each and every variable and how to understand the bouncing ball. The first variable I want us to discuss in bouncing ball is velocity. What we have to know about velocity, which is v initial and also v final. So what we have to know is that it will the ball will go up with a certain velocity. For example, it might go out with the velocity of 5 meters per second, and then when it goes out to the velocity of 5 meters per second, as the ball goes up, the velocity is going to decrease. So it's going to be 4, 3, 2, 1, until velocity decreases to a point where it is 0, which is known as the maximum height. Now because it has no velocity to use it to go up, now the velocity is gonna increase again. 1, 2, 3, 4, 5. So yeah, I want us to note one thing about the velocity. Say that when the velocity it goes up, the velocity is going to decrease as the ball goes up, and then it decreases to a point in which it is 0, and then the velocity goes up again as the ball goes down. What is making the velocity to decrease when the ball is going up and to increase when the ball is going down? It is what we call a gravitational acceleration. It's force of gravity, which is 9.8 meters per second, which makes it to accelerate backwards as the ball is going up. That's why it is decreasing, and which makes it to accelerate downwards while the ball is going down. That's why because it's always downwards, it has the influence of decreasing the velocity as the ball going up, and then it has the influence of increasing the velocity when the ball is going down, because it's always downwards. It's the force that the earth pulls on an object which is above its surface, and it pulls it towards its center. And then now, because the only force, or F net, which will be acting on all projectile, because a projectile is like an object that has been given initial velocity and moves under the influence of gravitational force only. So because F net equals to what? Equals to Fg, it will also mean that F net will be downwards, because Fg is downwards. And then what tells about F net? F net is directly proportional to what? To acceleration. So Newton's second law says that if a force acts on an object, the object will accelerate in the direction of the net force. So this is the net force is going downwards, which tells us that the object will also accelerate downwards. That's why we see it increasing speed as the object goes down. So that's why it increases speed. So what do we have to know about velocity? The velocity is that when the ball goes up, the velocity decreases as to until a point of 0 because of force of gravity. As the ball goes down, it increases up and then up until this velocity which it goes up with. What you have to note is that this is is like a parabola, because a parabola it has 2 points which are equal on both sides. There's 5 here, there's 5 here, there's 4 here, there's 4 here, there's 3 here, there's 3 here, there's 2 here, there's 2 here. That's how we have to deal with this problem, to say that if we record, we say a ball bounces to a 5 meter, the ball bounces 5 meter above the ground, and then we say now let's measure the velocity at 3 meters. At 3 meters there will be the velocity of the ball going up, and there will be the velocity of the ball going down, and then at those two journeys of going up and those two journeys of going down, we are measuring the velocity at a height of 3 meters, to say that when the ball passes this point, which is 3 meters away from the ground, what will be the velocity? We'll find that the velocity of going up will be the same as if the velocity is 4 meters per second going up. When it comes back, it will come back with what? 4 meters per second. That's what we have to understand, that here this velocity are at the same points. For example, the velocity that it was thrown up with, or the velocity that it leaves the ground with, it is 5 meters per second. It's gonna come back at that very same ground at what? At 5 meters per second. But what will be different is what? Is the sign. For example, let's say that up is positive. So if up is positive, it means that all the velocities going up will be positive, all the velocities going down will be negative. So because this one are going down, there will be negative, 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 negative. They have the same magnitude, but what? Opposite direction, which is just emphasizing what? Emphasizing the direction. So that's what we have to know about the velocity at this and where the velocity is 0, we mentioned that point as what? As the maximum height. A maximum height, that's where the velocity is 0, v equals to 0. So that's what we have to know about the velocity when it comes to this situation. Now we have described the velocity. Now let's describe the change in y, or the displacement of this, because the displacement is also very much important. So we have to know how displacement works in a bouncing ball. So we have cleared up space, we have described velocity. Now let's describe the displacement. So let me just draw the axe again of the bouncing ball. And there is one important thing that you also have to know about this, to say that this velocity, let's say it is 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. To say that when it comes to the velocity here, if it goes up with the velocity of 5 meters per second, it will come back with the velocity of 5 meters per second. But it will not be the case with this velocity of the next bounce. This is the first bounce, and then this is the when it leaves the ground here after the first bounce. So the place where it is in contact with the ground, it is this place. That's when the ball is in contact with the ground. And then we have to note that due to the ball being in contact with the ground, it's gonna lose some kinetic energy to sound when the ball makes a sound hitting the ground, and also some kinetic energy to friction as the ball scratches the ground, and then it will lose some kinetic energy in form of heat, because whenever there's friction, there's going to be heat. So because of it, it will also lose some kinetic energy, meaning that the velocity that it goes up with after being in contact with the ground is gonna be less than this 5 meters per second. Maybe it will go up with 3 here, maybe it will be 3, and then say 2, 1, 0, 1, 2, 3. You see, but what you have to know that, but when it goes up with 3, in the very same arc, it will come back with what? It will come back with 3, but they will just have the opposite direction, because now the ball is going downwards. So the velocity that it goes up with is the velocity that it comes back with in the same arc, because in the same bounce, because there is no air resistance, which where there's some kinetic energy will be lost, because here when the ball is in the air, mechanical energy is conserved, but here the mechanical energy is not conserved because W and C is not equals to 0. That's why here some mechanical energy is not conserved. But here we see that the sum of Emac is going to be equal to the Emac final. Emac initial is going to be Emac final in this whole in this whole movement. That's why we say already the velocity that it goes up with is going to be the velocity that it comes back with. So that's what you have to know. But because of some kinetic energy lost here, because of there are contact forces here, which will tell us that because there are contact forces, some energy will be lost. So now let's go and describe the change in y. Let me clear some space. Now, what do we know about the displacement or the change in y of this motion? The displacement or the change in y in this motion, you have to know that when the ball goes up to the maximum height, then it comes back to the initial position, the change in y going up will cancel with the change in y going down, meaning that the total displacement of this whole motion is equals to 0. Displacement focuses on what? It focuses on change in displacement equals to final position minus initial position, because the the initial position, it's here where the ball started. The final position will be where the ball ended, meaning that because it is at the same place, it's both at the ground at the same level, meaning that when you subtract things on the same level, displacement will be equals to what? To 0. So that's what displacement deals with. Going up will cancel going down. But sometimes they don't say what's the displacement of the whole motion. They will ask you from here, from the where the ball bounces off the ground to the maximum height, what is the displacement? Because now we are only focusing on going up. We will calculate the height from here to here, but it will only be 0 if they say the displacement from where it begins to where it ends. That's when the one for going up will cancel with the one for going down. But if they say to the maximum height, that's when now you can calculate it. So that's what you have to know, because the height of going up is equal to the height of going down. We'll see already. That's why they can cancel one another. If they ask you to calculate the height from where the ball started to the maximum height, you can just calculate the height from the maximum height to where the ball ended, because these heights will be, if x is this one is equals to x meters, this one will also be equals to x meters, because the distance are equal. So that's what we have to know about the displacement. And the second bounce after the ball is in contact with the floor will be a little bit smaller or a little bit lower in height as this as the first height. Because what? Because of some energy will be lost here because of heat, sound, and also friction. But sometimes they do tell you that the bounce is elastic bounce, meaning that no energy will be lost here. If there is no energy lost, they tell you that it is elastic. That's when all the bounces will be equal in what? They will be equal in the distance covered. They will be equal in velocity and equal in everything. They will be just telling you that no, here these bounds are basically the same parabola. So you have to deal with to say that, oh, because they're the same, this height will be equals to this height, because they are the same. And that's what you also do with the velocity. If you are told that it is the bounce is elastic, it goes up here with 5 meters per second, it comes back here with 5 meters per second, there will be no energy lost this time here. Because of friction, it will also go back in the second bounce with what 5 meters per second going up and comes back with the 5 meters per second going up, if we are told that the bounce is what is elastic. So that's what you have to note about what the information tells you. So now we are done with change in y. Now let's describe the change in time now of a bouncing ball. Okay, so now let's describe the change in time. Let me draw our bounces. So what we have to know about the change in time is that the time that it takes to go to the maximum height, which is this one, is the time that it will take from the maximum height to the end of the bounce. To say that if this is 2 seconds, this will be 2 seconds. So that's what we have to know about the time. It's like a parabola kind of, and also that which tells us that if they give you the time for this whole motion, to say that the time is 4, you just have to take the time for the whole motion, divide it by 2, and then you'll get the time for here and also get the time for here. So that's how we deal with the time here. But here, because some energy has been lost from from sound and heat, it will tell us it will take a little time. Maybe it will take 1,5, and then here it will take 1,5 seconds. Altogether, it's gonna take 3 seconds. So that's what we have to know about the time here at the bouncing ball. So we have described all the variables, which is the time, and also the change in y, velocity, acceleration. Acceleration is 9.8. Is 9.8 here, 9.8 meters per second, and it's always downwards. But what other books include it, but other books do not include it, to say that when the ball is in contact with the ground, that's a place where the acceleration will change for a split of a second when the ball is still in contact with the ground. That's why some graphs, you will see that when they draw an acceleration time graph, it will always be, for example, if you say that up, if you say down is positive, it means that the acceleration throughout the whole distance will be 9.8 meters per second squared, and then you will see it being constant. You will see it being constant, and then when it comes to a place where the ball is in contact with the floor, here there will be negative 9 meters per second squared. That's when the acceleration will go here to negative 9, negative 9.8 meters per second is the same magnitude here, but which means that the acceleration will be upwards, and then it comes back to a place where it is constant again. What does this thing represent? It represents this place where the ball is in contact with the floor. So what does this mean? It means that if down is positive, it means that if acceleration is downwards, it means that it will be positive. But if acceleration is upwards, it will be negative, meaning that this side, the graph is going to the negative side, because what is going to the negative side, because now the acceleration is upwards, meaning all the time where the ball is moving here, acceleration will be what? Acceleration will be downwards. But when the ball is in contact with the force, the acceleration is upwards to make the ball wanna go up, because there will be F net equals to momentum, change in momentum, and also change in time. So we'll see that this F net, which this momentum or the change in momentum here, will be upwards. So because the F net will also be upwards when the ball is in contact with the floor, that's when we see that the acceleration for the contact time will also be upwards, because F net is always in direction of the acceleration, as our Newton's second law says, you see that if a net force acts on an object, the object will accelerate in the direction of the force, meaning that because the change in momentum will be directed upwards, that means that the acceleration will also be upwards. So that's what we have to know about acceleration, but it's only in the time in which the ball is in contact with the force, with the floor. But at all other instances, we'll see that the acceleration will always be constant, having the direction downwards throughout the whole motion. So now we are done with the theory of the bouncing ball. Now let's go to solving some exam question papers on the bouncing ball. So they say that Masara throws, I think there's something which is missing here, throws a ball vertically downwards from the top of a building, as shown in the graph below. It took the ball 2.8 seconds to reach the ground. The ball bounces off the ground, reaching a maximum height of 8 meters. Ignore the effects of air resistance. And then it says that calculate the speed at which the ball is thrown downwards. So what I like to do before everything is just to draw my scenario so that I can know what's happening here. So here's Masara, and then Masara, they say they throw a ball. They say they throw it vertically downwards, and then when they throw a ball vertically downward, let's see, they throw it. Let me just do like this. Then when they throw a ball vertically downwards, they say the ball comes to a point where it bounces off the ground. So we are seeing that the Masara is here. They throw a ball, it bounces somewhere, and then it reaches a height of what? A height of 8 meters after the bounce, and then they throw it from a building which is what? Which is 48 meters above the ground. What else are we told? We are told the time that it reaches the ground with from the time it is thrown, which is what? 2.8 seconds. So that's what we know so far. Other things we have to just calculate. So let's come here. Calculate the speed at which the ball is thrown downwards. So whatever that we have to know is the first thing that I would like to do is to mention the section of motion that I'm going to use to say that which section of motion am I given variables of, which I can also apply. So I'm using the section of motion from which he throws the ball up until the time that the ball reaches the ground. So let me use this section. Let me draw the arc so that we can be on the same page. So it throws a ball from a certain height, and then that ball reaches the ground. So this will be our v final, our final velocity when the ball reaches the ground, and our v initial will be when the ball is thrown downwards. So we are not, for now, we are not dealing with this part of the motion now. We are dealing with what? With this part of the motion now, which is here. So let's name variables according to this now. We have to know each and every section of motion. So v initial, what is it? We are looking for it. This one, they say that there's a velocity at which the ball was thrown at the ground. V final, do we know it? We are not told v final. What else? Change in velocity, which is displacement. What we have to do is to also choose direction. Let's say upwards is positive. Upwards is positive, and then if up, which means that all things which are going up is positive, all things which are going down is negative. So the distance is covered by the ball going downwards at this time, because the ball is being thrown from high of a building going down, meaning that it's going to be negative. And then negative what? The distance which is covered from the height of the building going down is what? Is 48 meters. And then what else are we given? Are we given the time in which it takes from the height it was thrown here to the time where it is the ground? We are given the time is what? 2.8 seconds. And what is the variable that we also always know in vertical projectile? It's gravitational acceleration, which is always downwards. If now downwards is negative, is negative 9.8 meters per second squared. That's what we know about gravitational acceleration. Now, using all this information, can we find this? And then without final velocity, because we don't know the final velocity, let's check for formulas without final velocity. This one has final velocity, final velocity. How about this one? This one has doesn't have final velocity. We are looking for initial velocity. How about change in y? We have it. The change in time, we have it. Acceleration, then change in time, we said we have it. So let's use that formula, which is change in y equals to v initial change in time plus half a change in time squared. Then now let's just substitute our variable. One thing to remember is that when we substitute our variables, we substitute with our signs, and then v initial and then change in time. Let's substitute 2.8 seconds and then plus half into negative 9.8, and also here change in time is going to be 2.8 squared. And then now we group like terms, and then this is going to be negative 48, and then this side is going to be positive half into 9.8 into 2.8 all squared divided by what? Divided by 2.8. And then the answer is gonna be, let me press my calculator, negative 48 plus half into 9 over 9 over 8 into 2.8 squared, and also over 2.8. So the velocity that we got here is that we got negative 342 meters per second, and then we say that upwards is positive, meaning that downwards is negative. So this sign, we're gonna change it to be what? To be downwards. And look at it, the ball was thrown going where? It was thrown going downwards, meaning that here our velocity, let me just wrap here because now we know the answer. Wrap here, and then as our answer we are going to write a negative 3.42. Yeah, and then here the velocity is gonna be what? Negative 3.42. Yeah, so now let's solve the next question. Let me just make some space here so that we can work. Okay, yeah, and then what does it say? That the speed in which the ball hits the ground. So this is gonna be simple, because now here the speed that the ball is gonna hit the ground, we are looking for the final velocity. We have a lot of bunch of variables that we can use to get the answer, because we can use this formula, and we can also use this formula to find v final, and we can also use this formula to find v final. We just use a formula that we want, but let's just use this one, which is not complicated, equals to v initial plus a change in time, and then we are still using the same set of motion from when the ball is thrown to when the ball reaches the ground. We are looking for what? V final, the ball which it is, the speed which it is the ground with. Initial speed, we substitute it with this sign, the one that we got there, and then plus into negative 9.8, and then change in time is 2.8 seconds, and then we press our calculator, and then it's gonna be negative 3.42 plus into negative 9.8 times 2.8. This gives us 30.95 meters per second, and then it's also negative, meaning that it's gonna be 30.95 meters per second squared, where downwards it's gonna hit this the downwards, it's gonna hit the ground going down. So we also have this speed here. Let me rub here so that I can write the speed here. Write the speed, which is 30.95 meters per second. So let me wrap here so that we can continue. So now let's go and look at the speed which the ball bounces off the ground. So we must note that the ball was thrown from a height, and then when it was thrown from a height, it reaches the ground here, and after it reaches the ground, it lifts off, and then it reaches a point above the ground. So we must know that in the introduction, we're dealing with bounces that were like this. In the introduction, I spoke about bounces which were like this, but now we are dealing with bounces which are like this. What's the difference here? Is the contact time, the time that the ball stops on the ground. So here they are saying that ignore the what? Ignore the effects of air resistance and the contact time. So here we are just treating this section as if the ball did not spend some time in the ground. We are dealing as if that it hit the ground and came up at the same time. So that's why they say that we must ignore the contact time, that the contact time is zero. There is no time that is spent on the ground. So that's how this problem is formulated. So that's how we also have to deal with it. So now, because we are looking at the velocity that the ball bounces off the ground with, now this is the set of motion that we are using. This is the set of motion. Why is it important to draw out the set of motion? At first, I draw out the set of motion here. Now I am drawing out the set of motion. I want us to be able to use variable to say that all these variables, we cannot use them. We cannot use them to calculate what. We cannot use them to calculate the velocity that the ball bounces off the ground with, because we agreed that the velocity that it hits the ground with is not equal to the velocity that it goes up with. These are two different arcs, or are two different bounces. So this information, we cannot use it. We have to find information from when the ball leaves the ground and reaches some point above the ground. That's why I like to isolate section of motion, so that I can name my variables according to the section of motion that I'm dealing with. So now I'm dealing with this section of motion here, where the ball leaves the ground and then reaches a point above the ground. So this will be my V initial. When the ball leaves the ground, I'm looking for it, and then this will be my V final when the ball has reached a certain height above the ground. So here the trick is that they want you to they want you to be able to spot out variables. Let's read out the information again, and then there's a variable I want us to spot. First, let me list the ones that I have now. V initial, we are looking for it, and then V final here is the one that we are going to spot in the information, so that what's the velocity here, and then change in Y. They were told that it reaches a maximum height of 8 meters in a second bounce, which is also this 8 meters here. And now it reaches it going up, where we said up is positive, meaning that because the ball now is going up, this is gonna be positive, but it doesn't matter whether you write it or not. And then the gravitational acceleration is always downwards, which is negative 9.8 meters per second squared. And then that's what we have. So I want us to spot the final velocity here, the velocity here at final, using the information. So that Masara throws a ball vertically downwards from the top of a 48-meter tall building as shown in the graph below. It took 2.8 seconds to reach the ground, and the ball bounces off. So we are dealing with this section now after it bounces off the ground. They say when it bounces off the ground, and then they say that reaching a maximum height of what? Of 8 meters. So meaning that here, when it had reached 8 meters, the velocity was 0, because always at maximum height we say that velocity decreases to a point where it is 0. So here at v final, velocity is going to be what? It's going to be 0. Now, knowing this and this and this, we can solve for this. Let's find the right formula. This one has change in time, we cannot use it. And let's check this one. It has everything that we have, so we are going to solve the v initial in that formula. So that was the trick there, to know that the 8 meter is taken as what? The maximum height. Then you say v squared, and then plus 2a change in y, and then you substitute everything which is sign. V final is 0, the one that we just found, v initial, and then v initial we are solving for it, and then we also solve for put negative 9.8 here into 8. So let me just find space here, and then it says that 0 this side, and then it's gonna be v initial squared plus negative 2 9.8 into 8, and then now I just take this side, then it's gonna be 2 into 9.8 changing and then square root both sides, these 2 cancel these 2, and then it's gonna be equals to plus or minus. Every time we do an inverse, it has to be plus or minus into 9.8, and then there will be 8, and then we solve our answer. Let me press my calculator. 2 into 9.8, and then there will be 8. Then my answer is 12.52 meters per second. And then it because the ball was going up, now when it was bounces off, we choose the positive side, and then the answer is what? The answer is gonna be 12.52 meters per second, where upwards when it bounces off the ground. So this is what we have to know. Thank you for watching this far. If you have reached this far, be sure to press the like button and also to subscribe. Thank you. I will see you in the next video when I deal with problem type 5, and then we go on to the vertical projectile motion graphs. Thank you.